Okay, so whoops. Oh, goodness. All right. So we're going to talk more about hashing and hash tables today. We're going to begin by talking a bit more about hash functions and what makes for a good hash function and some hash functions that are used in practice. And to think about certain ideas that are incorporated in practice into hash functions, we're actually going to have to spend a little time thinking about data representation at the level of bits, ones and zeros. So last time we talked about how the Java string object has a hash code that's defined in terms of taking each digit and multiplying it by 31 to the power of the array index where it's located. So that works pretty well for dispersion, but it's kind of expensive to calculate. It takes a fair amount of operations to calculate exponentiation, and there are some tricks one can use to speed it up, but it's fundamentally kind of slow. So in more recent years, hash functions that can achieve a good dispersion with less expensive arithmetic operations have become more popular. And one of the arithmetic operations that winds up being crucial in many of these applications is known as XOR, or exclusive OR.
I've heard of okay. I know there's a variation of this called exam, XOR, and AND. Those are
exclusive AND is not really relevant here.
Yeah, I know. It's just something that I thought of. Right?
So what does exclusive OR mean? We can think about it in relation to AND and OR. So you all might remember, so we're going to build like a little truth table to illustrate these things. So if I've got two Boolean values, A and B, there are four possible combinations. So the four combinations, right, are both are true, both are false, A is true and B is false, A is false and B is true. And these are the operators that we are accustomed to using in Boolean conditions. So first we'll look at A and B, and that's true if both of them are true, and it's false otherwise. And then A or B is true if either of them are true and false otherwise. So now we're going to look at exclusive OR. So if both of them are false, exclusive OR is false. Something's got to be true for exclusive OR to have something to work with. If either of them are true, then exclusive OR is true. And at this point, it just looks an awful lot like OR. But now we get to the exclusive part. Exclusively one of them has to be true. So if both of them are true, exclusive OR is actually false. So in a way, exclusive OR often corresponds maybe a little more closely to our typical intuitions about the idea of OR. That is, it's one or the other, not both. That's exclusive OR. So why do we care about it for hash functions? Well, consider this. If you were to imagine the representation of any data type as just a sequence of bits, and here, just to illustrate the principle, we'll use just 4 bits, so something like 1101. And now imagine that you were to repeatedly do ANDs over and over again with completely random strings of bits. So maybe you AND with 1011, and then after that you AND with 0110, and then after that maybe you AND with all ones. Well, as we keep anding, we're going to see an interesting phenomenon. So when I look at the first two, I get one, oops, I only have one result of the and. I get 1, 0, 0, 1. So I'm doing what's called bitwise and here. That is, I'm looking at the individual bits in the binary string and anding them independently of each other. Right? And so now I'm going to and my 1, 0, 0, 1 with 0, 1, 1, 0. And when I and them, I get a 0, a 0, a 0, and a 0. And then when I and it with 1, 1, 1, I continue to get just like all zeros. Now, I'm hand waving a little bit here, but the general idea I think you can see is that if I start with some arbitrary string of bits, and then I start anding it with other random strings of bits, eventually it's going to turn into all zeros. The zeros are just going to keep pulling everything down. Now, if I treated the same bit string but with OR, we would see an inverse phenomenon, right? So let's say I have the same bit strings, but I'm ORing them now. So if I OR those first two, I'm already at 4 ones, and at 4 ones, I will indefinitely remain. So combining bit strings with these bitwise and OR operators tends to have bad dispersion properties because it tends to pull the values to one extreme or the other. And this is where exclusive OR actually gets a little more interesting. So let's imagine we were to exclusive OR these values. So if I, whoops, don't know where that came from. Go away. If I were to exclusive OR these values, I get 1 XOR 1 is 0. Whoops, come back. Really, come back. 0. And then 1, 1, 0. So I've exclusive ORed 0 and 1 and gotten 1. 1 and 0, I got 1. And 2 ones, I got 0. So now I'll exclusive OR with the next value, which happens to actually be 0, 1, 1, 0. And so here, I'll actually get all zeros. Then when I exclusive OR with 1, 1, 1, 1, I get all ones. But now if I imagine putting in other random bit strings like 0, 1, 1, 1, now I'm back to 1, 0, 0, 0. And I could imagine throwing in another random string of bits. Humans are really bad at generating random numbers, by the way, and I'm just proving that for you, for your amusement. You get 1, 0, 1, 1. The point is, with exclusive OR, as you keep throwing in random bit strings, you keep getting interesting results that are dispersed across the space of possible binary values. So it doesn't have the gravitational pull that and OR have. Something else then that's appealing about exclusive OR is that it's readily implemented directly in hardware. In other words, I don't necessarily have to write code to implement exclusive OR. I should back that up a second. I shouldn't ever have to write code to implement exclusive OR. Exclusive OR is routinely implemented as a hardware instruction.
Is it?
Yes.
Because I know it's not a perfect analogous reference, but it's a nice point. Exclusive OR is kind of commonly used in redstone functioning in Minecraft. I'm sorry, I'm just comparing it to something.
Redstone functioning in Minecraft.
Yeah,
my Minecraft expertise is not up to the challenge.
Yeah, but some people can actually make computers with the concepts provided from and or and XOR.
I've heard about that people essentially build a simulated computer using Minecraft operations. Yeah. Okay, so if it's helpful to you, great.
Yeah, it's just something I compare.
Mm-hmm. Yep, very cool. So that's exclusive OR. So I went over all of this because many contemporary hash functions, in order to be efficient, will use exclusive OR to combine elements of a string into a hash value. So let's think about how this might work in a really simple form. So, and this simple form isn't all that great a hash function, but it illustrates the principle that we're looking at. Let's imagine one of our examples from last time, ant. And so A was, we're going to represent these with 5 bits in order to capture the 0 to 25 range. So we have A, which is 0, 0, 0, 0, 0. And we figured out it was 13 last time. Was that right? Yeah. So 13 is, there are no 16s. There's an 8 and a 4. That's 12. Yeah. So that's 13. And then T is what? 20? Or 19? So easy to lose track of these. Let's see. Well, if Z is 25, Y is 24, X is 23, W is 22, V is 21, U is 20, T is 19. Yeah. So that's a 16. So we've got 3 left. All right. So this is ant, and we can imagine combining these with exclusive OR. So the A exclusive OR N is actually just going to be, it's going to look an awful lot like N. And then and then the AN exclusive OR T, 1 exclusive OR 1 is 0, 0 and 1 is 1, 1, 0 is 1, 1, 0 is 1, 0, 1 is 1. And so this is a combination of those values. Let's see if it's permutation invariant. So we're going to try to give our ant a tan. So when we do that, we will have 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, and 0, oh, 0, 1, 1, 0, 1. There we go. So the first two, 0 is an identity element, so we just get 0, 0, 1, 1. And then we get 1 exclusive OR 1 is 0, 1, 1, 1. Whoops, I messed it up. Let's try that again. 1, 1 is 0, 1, 0, 1, 1, 1, 1, 0, 1. And it turns out they're the same. And then it turns out that, in fact, exclusive OR is what's called a commutative operator. It doesn't really matter which order you do it in. So you still need to combine this with some other kind of operation. So here's an example of how you might do that. You could do a bit rotation. So let me show you all what that entails. Let's imagine we exclusive OR the first 2 values. So as we saw before, we got 0, 1, 1, 0, 1. Now what we'll do is we'll rotate the bits to the left. So we get 1, 1, 0, 1, 0. In other words, for each of these bits, I move it 1 position over, and then the bit on the end gets moved all the way back around. So now I can exclusive OR this with 1, 0, 0, 1, 1. And that gets me 1, 0, 0, 1, 0. And then I'll rotate it to the left, and I get 1, 0, 0, 1, 0. Now I'll do the same thing with tan. So I take this first result over here, and I'm going to rotate it left, and I get 0, 0, 1, 1, 1. And then I will exclusive OR it with 0, 1, 1, 0, 1. And when I do that, I get 0, 1, 0, 1, 0. And when I rotate that to the left, I get 1, 0, 1, 0, 0. And notice that these two now differ. So the point of that is I can take this exclusive OR idea and combine it with another very cheap, easily implemented in hardware option. Why are you doing your physics? You're in the computer science class. Okay. You can take it, combine it with a cheap hardware option, and get much more efficient hashing in practice. Now, the thing to keep in mind about hashing is that inevitably there are always massive subtleties here that involve easy mistakes that one can make that cause the dispersion to not be very good. So hashing continues to be studied with great enthusiasm by computer scientists, and people are often coming up with new hash functions, and then other people are often coming up with ways to show that those new hash functions don't always work very well. People will often come up with really clever counterexamples and the like. So one technique to try to deal with this is to have large hashing benchmarks of common data sets that you can try to combine with different hash functions to get a sense as to what the dispersion looks like. With that background in place, then, I'm going to introduce you to a couple of interesting hash functions. There we go. So a very popular hash function that's heavily in use at the moment, and here I'm just going to show you the pseudocode from the Wikipedia page, is known as FNV1. And here's how it works. It starts by initializing the hash value to a special value called the FNV offset basis. In other words, it's just a really big integer constant that's selected because when you perform these operations on it, you tend to get good dispersion. So for instance, 0 would turn out to be a fairly bad value to start with. And you'll see why in a moment. So then have a for loop over each byte that needs to be hashed. So notice that this really can work with any data structure, because in principle, any data structure can ultimately be interpreted as a long string of binary digits. There have to be bytes in memory that it's occupying, okay? So for each of those bytes, you multiply the hash value by a carefully chosen prime number. Any guesses as to how prime numbers get involved here?
Because prime numbers can't be divided.
Okay.
Well, they can't be divided cleanly. I know that much.
In other words, they have only two integer factors, themselves and one.
Yeah.
If you try to divide it by any other integer, you get a remainder.
Yeah.
So how might that help with hashing, do you think? Yeah, Paxton.
Because you're using mod.
Mm-hmm.
So the remainder is, if it was not a prime number, then if you tried to divide it and got something that wasn't a remainder, mod would give you 0.
Correct, and that's a good point, because ultimately, we're not going to do an explicit mod here, but ultimately the value that we get out needs to be modded by the array size. So that does turn out to be an important idea. What's really great about big primes is that it's hard to get a repeating sequence because the primes are big and don't have underlying divisibility. If you multiply by a large composite number, you can often get a repeating sequence based on its factors. But with a nice big prime, that's a way to avoid that. So they multiply it, and then if the multiplication overflows, they just throw away the extra bits. And then they exclusive OR it back with that original byte of data. Part of how this scheme works is the hash is expected to be a 64-bit integer. So 64-bit allows for a large number of possible values after the multiplication. The exclusive OR, though, only happens with the low order 8 bits because we're only hashing 1 byte of data at a time. So in effect, what happens is that byte of data is actually used to help scramble itself via exclusive OR. Yes?
This is just a weird thought I thought of, and it doesn't truly pertain to the topic, but the concept of bits. Is that why certain software is called 64 and 32 bits?
Oh, that's a great point. Actually, a very pertinent observation. It's not so much the software that's 64, 32-bit as the CPU. So when you're thinking about at the hardware level, everything we do ultimately gets compiled down to machine level instructions. And in the computing organization class, we learn about that in tremendous detail. Like we will design a CPU and we will design a machine language for it, and we'll write programs in machine language in that class. It's a lot of fun, really. I'm not being sarcastic. I love that stuff. It's fun for small programs. I wouldn't want to build a big program that way.
Most definitely. I'd rather have
Yeah,
a language.
that would be challenging. But when we're talking about machine level instructions, by the nature of a CPU, the CPU can only have a certain finite number of wires coming in that denote the binary digits upon which it performs arithmetic. You know, it has to be a finite number because we don't have infinite space for our CPU. So if I say I'm using a 64-bit CPU, put your calculator away, please. If we're using a 64-bit CPU, what that means is that the machine instructions perform arithmetic 64 bits at a time. Back in the day of the Commodore 64, I had an 8-bit CPU. So at the machine instruction level, it could only perform operations on values from 0 to 255 or negative 128 to positive 127.
Wait, then why a 30? Okay, so here's that dumb question.
Okay.
Why an 8 CPU, not 64?
So back then, I mean, you have to have a limit.
Yeah, I know there has to be a limit. That's not
So back then, what we were able to engineer was most practical and cost effective at 8 bits. Now, of course, you want to do math. Yes.
How come they've been on 64 bits? So the calculator hasn't gone to 128?
64 bits turns out to be pretty good for most math you would ever do. There are exceptions. There are times you want more than 64 bits with cryptography in particular. But yeah, you could certainly in principle go to 128, but 64 has proven useful. Yeah.
I'm guessing those big mainframe computers, like the stuff they
Yeah.
store, the stuff they store at like Google, the one they have has a lot more bits.
Well, the CPU is still just 64 bits. It has a lot of RAM.
Well, no, go figure. Some
Yeah.
of the calculations they make for that is incredibly complex.
Yeah. So in any event, we can do 64 bits at a time at the machine level. Now, back on my Commodore 64, of course, at times you wanted to do math that needed more than 8 bits. So what you have to do is just do the math repeatedly, right? So if you're adding two 16-bit numbers and you've got an 8-bit CPU, you first add the two lower order 8-bit numbers. And when you add them, you may have a carry. And so you carry that bit and then do the addition again with the next group of bits. And so in a language like Python that has arbitrary length integers, because in Python, there's no upper limit to the size of the integer aside from the computer's memory. How's that implemented? Well, it's really just an array of integers. And every time you overflow, it just sticks another integer on the end. So it's not actually all that difficult to implement, but it is certainly an interesting approach to take.
So like in this case, say the overflow is like at 8 numbers.
Yeah.
So, and you do like a 9 number, so like 1, 2, 3, 4, 5, 6,
Okay.
7, 8, 9. Each number in that spacing is just.
Well, you either carry the overflow to the next part of the math or you throw it away and you decide I'm done. And that can happen too. There are times where there's just a certain range you can handle and that's that. We leverage that here by saying all we really want is that single 64-bit integer because ultimately it's just going to turn into an array index. So we don't even want to keep the extra bits, so we throw them out. And as a rapid operation, we're taking advantage of that here with this FNV hash. So this is one example. And the reason I'm bringing up this specific example is in a few minutes, we're going to bust out the hash cards again. And this is one of the hash functions that was used to calculate the values there. Here's the other one. It's known as Murmur. And Murmur is pretty intense. It operates on 4 bytes at a time. It has a whole bunch of specially chosen constants that are used to ensure some good dispersion. And then it does a lot of things. So it starts with a 4-byte chunk at a time. So it takes 32 bits at a time, multiplies it by the first constant. So these are numbers in what's called hexadecimal, base 16. And hexadecimal is really nice for talking about bit strings because 4 bits is 1 hexadecimal digit. It's a lot more compact. Once you're working at kind of the low bit level and thinking those ways, hexadecimal is just a beautiful thing. Yes?
Is that how chunk coding works like if you just say you've got a map that has to load, but it will load in pieces at a time.
So ultimately those pieces are binary, sure.
Yeah, that's what I'm saying. Is it chunk? Is this kind of a good example of chunk coding?
Not really, no.
Okay, I didn't know.
So it multiplies by that, and now we've got that rotate left operator I was talking about earlier. So it does the multiplication, rotates the bits to defeat the commutativity of multiplication. Then it multiplies by another constant. Then it exclusive ORs it by the 4-byte chunk itself. So it exclusive ORs it back by itself. Then it rotates it left 13 positions. And the first time it rotated it left 15 positions. And then it multiplies it by yet another constant and then adds this constant over here. Then after it's done all of that, it exclusive ORs it with its length. So how many bytes there were to begin with. Then these are shift operations. They're similar to rotates, except that when stuff goes off the end, it doesn't get rotated back around, it just gets filled in with zeros. So it exclusive ORs it with itself, shifted 16 bits to the left. So it takes half the string and exclusive ORs it back with itself. And then takes another piece of it, exclusive ORs it back with itself after doing some more multiplying and so forth. So this looks royally convoluted, and in a way it kind of is, but I wanted to emphasize how its ingredients fundamentally make sense as a way of scrambling numbers and dispersing them. Multiplying by large prime numbers, scatters them around, takes advantage of the overflow. Whenever you overflow, you're effectively just keeping something of a remainder or a residue, as they would say in abstract algebra land. Actually thinking about this stuff rigorously requires massive amounts of abstract algebra. It may have the word abstract in it, but it turns out to be really practical when thinking about this stuff. And then we have our exclusive ORs, rotates, and shifts. And these are all ways of defeating commutivity so that however you permute them, you get different hash values every time. So those are 2 examples of fairly widely used hash functions. So I'm going to go ahead and distribute these cards again. Let's see how many people we got today. Second. 1, 2, 3, 4, 5, 6, 7. Oh, there we go. So let's see.
What do you, Sarah, just share that there.
So I'm going to distribute 9 cards to each of you. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah.
And should be 9 come down. So lay out your numbers 0 through 7. And we're going to do some hashing. We're going to do it a little differently this time. So last time, when you laid out your cards and they had a collision, what you did was you built up a chain. I want you to do something different this time. Every time you have a collision, what I would like you to do is actually just move it one square to the left. And if you wrap around, if you're all the way on the left at 0, then move it all the way around to the other side, and then stop when you've added 8 items. And use the colored in number. So the number on the left, that's going to be the hash code generated by this Murmur algorithm. Yeah, so these cards have a word and a hash code for the word. So this one goes at that cell. Then this one goes here. But this goes here, so they have a collision. So you're going to move it one to the left, or left is this way. And so just keep doing that until you run out of space. So we're only going to allow one card per cell. Go ahead, sort those out.
Question, what if you get a collision at the right?
You always do, you just keep going left until you find an empty spot. And then eventually you're going to run out of space. So, as you all did this, how many spaces did you sometimes have to hop to find a home for something?
Sometimes it happens. I have like a couple.
2? Paxton, what did you typically have? How much hopping did you have to do to find a spot typically?
Typically like 3 or 4, but I just did one for 6.
What's that?
I just did one that was 6, but.
Oh, okay. But towards the end, of course, it's going to escalate a lot. How about you, Ivy? 3 or 4? So this is a different hash table implementation known as open addressing. So let's kind of talk a little bit about open addressing and what some of its benefits and drawbacks are. You have already experienced a major drawback of open addressing. And that is, with open addressing, the philosophy is when you run out of space, or when your space is occupied, you have a collision, just look at the next spot and put it there. So in effect, you wind up having something similar to chaining where you do a lookup, and when you go to a spot and it's occupied, but the keys don't match, then you just keep looking at its next neighbor until you run out of, until you hit some open space. So linear probing is what this looking for the next cell is called, and there are other approaches taken as well. There's what's called quadratic probing, where you do like the square of the distance and stuff like that, but that's not super important here. What is important is the idea of a hash table that doesn't use an auxiliary data structure, that does everything right there in the array. If you don't have collisions, of course, it's beautiful. You don't have any pesky linked lists to think about. Certainly they felt pretty pesky yesterday, I think those linked lists felt. But it also has the advantage, though, of being friendlier with the memory hierarchy. So by having everything just in this top level array, you have fewer cache misses when you go looking for things. And so aficionados of open addressing point to this as a major advantage of the scheme. Disadvantage, though, is it can get almost pathologically bad when resolving collisions, because especially as your table gets more and more full, you might have to search an awful lot in order to find what you're looking for. So if you've got really good dispersion and a hash table that has a relatively low load factor, it can work pretty well. If I'm using open addressing, I'll tend to prefer a load factor that is considerably lower than the 0.75 we were using the other day in order to maximize how much space I have available. Now, this idea then has been taken to its logical conclusion in what is called cuckoo hashing. So I want you to leave your 0 through 7 in place, but gather up the rest of your cards. And we're going to take a different approach this time. Move your 0 through 7 so that it's possible to put cards on either side of each number, so both above and below the number, okay? So this approach, cuckoo hashing, is named after the behavior of a certain species of cuckoo birds. Anybody know anything about the nesting habits of cuckoo birds? So one thing that cuckoo birds are known for is scouting out to find nests that are unguarded when a bird of a different species is going to get food. The cuckoo bird then comes to the nest, kicks out one of the eggs, and lays its own egg there, and then flies off, leaving its cuckoo chick to be raised by this other bird. It kind of is a gremlin, yeah. So cuckoo hashing takes the same approach with a hash table. Instead of one array, we're going to have 2 arrays. So here's how I'd like you to hash. First, use the leftmost number to hash below. When you get a collision, use the rightmost number to hash above. If you get, and if a cell is occupied, you kick it out and hash it back again with the other number. Try it out. Let's see what you get.
So the cell's occupied on the top, we kick the top out?
Either side. Yeah. So whenever you've got a collision, you kick out the occupant and then hash the occupant on the other side with the other hash value.
Do we do it by the first number and the?
First number will be your bottom and the second number will be your top.
So basically, and then toss this back here.
Where's that one gonna go?
What do we do if it's occupied in both spots?
Well, if it's occupied, you just kick out whatever's there.
Okay.
And now it was a 7, so now you use its 3 and put it there.
Okay.
Yeah. All right. So, okay, we're almost done. Cuckoo hashing. So cuckoo hashing has some interesting pros and cons, right? On the plus side, the collision resolution often is pretty elegant. On average, it's actually just going to be constant time to do an insertion or removal. I didn't even talk about removal in open addressing. Boy, is that nasty. Because, of course, you've got everything at displaced. And so what you wind up having to do is mark it as removed, but leave it there. Then you can replace it later on if possible, whatever. But yeah, cuckoo is kind of a fun, elegant approach. The downside is that you need this extra array. And so you wind up having,
Extra memory storage.
yeah, it needs some extra memory. What do you all think of the cuckoo approach? Now, another disadvantage is you need 2 hash functions. The 2 different hash functions doing drastically different things is essential for cuckoo hashing. And the reason it's essential is that when you do your eviction, it really needs to wind up somewhere completely different so that you've got a very low probability of having some kind of crazy, degenerate, infinite loop happening. So for this to work, you have to have really good hash functions that are going to get you really good dispersal. In fact, an approach often taken in practical implementation of something like cuckoo hashing is to have a scheme for automatically generating new hash functions. Now, what might that look like? Well, you can imagine looking at something like Murmur and having a family of hash functions based on a sequence of constants available for each of these. So you can imagine having a sequence of good constants such that if your current hash functions aren't working, you can generate brand new hash functions by grabbing another prime from the sequence or whatever. So in that sense, cuckoo hashing winds up being quite a bit more complicated than the other schemes we were looking at, because you have to be thinking very carefully about the nature of the underlying hash functions. You can do some clever things to make cuckoo hashing even more effective and to waste less space. For instance, there are schemes where instead of 2 arrays, you could actually use 4 hash functions and 4 arrays. And by doing that, the incidence of collisions tends to fall a lot because you've got 4 different hash functions and 4 different possible destinations. So it's a little more complicated to implement, but kind of a lot of fun to do. So that's cuckoo hashing. Any questions on it?
No.
So yeah, so Dr. Goodrich generated these hash values from the animal names that you have there by using these 2 hash functions that I briefly showed you today. So that's hashing in general. I want to talk about another issue that arises with hash functions that is kind of beyond the scope of the depth at which we're going to think about it in this class. Yeah, go ahead and gather up your cards. But which is important as a practical issue in terms of security concerns. So in computer security, there are different kinds of attacks that can be mounted on software. And one of the most important kinds of attacks is called denial of service, or DOS. Denial of service attacks are very popular attacks because they don't require breaking any codes. To get a feel for what a denial of service attack is like, just imagine some company has a website up and you, the attacker, decide you want to keep people from using their website. So you write a program that constantly makes network requests at their server at such a large volume that the server becomes overwhelmed. That's an example of a denial of service attack. Now, why would somebody do this? One common reason is blackmail. So an attacker, for instance, might say, wire this amount of money to this Swiss bank account or I will launch a denial of service attack. They don't pay the ransom. The denial of service attack begins. They pay the ransom. The attacker backs off. Until next time, of course, because we all know how good it is to negotiate with terrorists. Yeah, Elijah.
That's what DDoS means?
Yeah, so DDoS is distributed denial of service, because a counter to a denial of service attack is if you're getting all the requests from some program on a single machine, it's quite easy to block that IP address from your server. And then
That's why I'm guessing that's why distributed DDoS works as a counterbalance because you
Right.
can send it to multiple machines.
right, it's a countermeasure. So if you've got lots of machines distributed that are all attacking it, that's a distributed denial of service attack. That's at the network level, but bizarrely enough, denial of service attacks can also affect hash tables. That is, if you happen to know A, that a particular piece of software uses hash tables as some part of its critical loop, and B, you happen to be able to determine a pattern in the hashing algorithm, you can deliberately load it with keys that cause its performance to degenerate by causing lots of collisions. So doing that can slow down the hash table and cause it to exhibit really bad, even linear time performance. And when you're expecting constant time performance from the thing, that's a huge problem. So in order to address this, there are families then of what are known as cryptographically secure hashes. So a cryptographically secure hash tends to be resistant to denial of service attacks because the dispersion pattern is really, really hard to predict. So with certain hashing algorithms, it's relatively easy to predict. And you can imagine an attacker doing experiments to figure out how to overwhelm a particular piece of software by feeding it keys that follow particular patterns and then seeing if its performance degrades. So you don't even necessarily need the source code to do this kind of an attack. So a cryptographically secure hash resists attacks of that kind because it's just that good at scrambling things.
It's random by nature.
It's not random, it's still deterministic. Random hashing would be kind of a disaster because then you wouldn't be able to predict which cell your value winds up in. They must be deterministic. If I hash hello, that hello had better turn into the exact same integer every time. Otherwise, if something random happens, hello suddenly goes from slot 2 to slot 27, and now I can't find it. So the hash function must be deterministic. But a cryptographically secure hash does really clever mathy things, so to speak. I'm hand waving here. But it does really clever things to keep itself secure from that, and from that kind of an attack, and be really hard to predict. So there's an analogy here with how a pseudo-random number generator operates. A computer doesn't generate truly unpredictable numbers. They're generated from a formula. But if the formula is really good, it's really hard to guess what the next number is. The same principle applies for a cryptographically secure hash.
How do you explain random? Math.random.
It's not random. It's just a function. So maybe we'll talk about this a little bit next time. But at its heart, a pseudo-random number generator just takes some value known as a seed, adds some value to it, multiplies by some other value, and bam, you have a new number. So if you choose these values really carefully, the sequence is very hard to predict. Math.random is nothing more than that. I mean, it might be a little more than that, but conceptually, that's really all there is to it. And cryptographically secure hashes rely on similar ideas. Now, they tend to have a big disadvantage, which is they tend to run slowly. And so they can often be kind of crippling for a hash table, whereupon you begin to wonder, well, why not just use a trie? So it goes. In the world of data structures, there are no single absolutely correct answers. There are different algorithms and data structures that just have different trade-offs. Let me remind you that for tomorrow, by tomorrow evening, I want you to submit the first part of Project 4, and I'll have a link up in Moodle for you to do that.
First part of Project 4
Is due tomorrow, yes.
what part is, what is that, like step 1, 2, 4?
So read Project 4 and do the first part. I went over it in detail in class.
Oh, Project 4 is already submitted.
It's
on the,
I went over it in class.
Okay.
All right. So very good. Let's go ahead and hand me your cards, and I will see you all on Friday.